Okay, so let's understand the next terminology. That next terminology is the fifth one, that is time period. Okay, now what is time period? As we say that the frequency is something, the number of cycles completed in every 1 second represents the frequency. So the frequency represents in 1 second, that is with respect to time, how many cycles are getting completed. And the time period is something which represents that since the cycle is getting completed. So what we can see here, from maximum to minimum, then minimum to maximum, this situation happen, this particular situation, which this process, it is also taking some time. So how much time basically this process is taking, that is how much time in one oscillation is taking, how much time is required for one oscillation to complete, that is represented by the time period. So time period represents, it represents the time taken by one oscillation to complete. So how much time is required by one oscillation to complete, this is represented by the term time period. Okay, so time period is basically, it is represented by a capital T like this. Okay, capital T represents the time period. Now you can see here the pressure from this maximum point moves to this minimum point and then again moves to this maximum point. So the time required for this kind of movement from this to this and this time is known as the time period. So it represents the time taken by one oscillation to complete. Okay, or we can represent time period in one more way, that it is the time taken by two crest or trough to pass or to cross a fixed point. Okay, it also represents the time taken by two crest or two trough to cross a fixed point. Now what does this mean? See, for example, I take this point. Okay, I take this point, let's say this point. So first crest will pass this point, and after the passing of this first crest, after how much time the second crest will going to pass this point. This will represent the time taken between these two, the time elapsed between these two crossings will going to represent the time period. Okay, the wave is moving like this, in this manner the wave is moving. Okay, the pressure is variation, the pressure variation is happening in this manner. So first crest will pass this point at some point, okay, pass this, cross this point at some point of time, and after the crossing of this first crest, after how much time the second crest will going to cross this point. Okay, this time will represent the time period, and similar can happen with the trough as well. Okay, in how much time the two trough crosses a fixed point, this will going to represent the time period. And similarly we have the last terminology related to this is wavelength. So what is the wavelength? We understood this term. The distance between two crest or two trough is known as the wavelength. Okay, so you can see the distance between the two trough, this will represent the wavelength, and wavelength is represented by the lambda. Okay, we studied this concept, lambda. Similarly here also the distance between the two crest or two trough, this is represented by lambda, this is known as the wavelength. Now we can also define lambda in one more manner, or the wavelength in one more manner in terms of the time period as well. Okay, so how to define this wavelength in terms of time period? We will say wavelength is basically, it is the distance traveled by a point on, okay, or by a crest or trough. Let's write it like this, it would be easy to understand. It is the distance traveled by a crest or trough, okay, it is the distance traveled by the crest or trough in time period t, okay. So the distance that crest or trough travels in t times, okay, in t units of time, will be known as the wavelength, okay. So what you can see, wavelength is basically a length. The unit of wavelength can be meter, centimeter, miles or anything depending on the type of wave we have. So there are small units also available, that is nanometer, micrometer, angstrom, and in such a way the wavelength can be represented by different units, okay. So what we can say wavelength is, either you can say it is the distance between two crest and two trough, or it is the distance travelled by the crest or a trough in time period t, okay, in t seconds or t units, how much distance is travelled by a crest or a trough will going to represent the wavelength, okay. Okay, so this completes the different terminologies related to the pressure variation and the density variation in the sound waves, okay. So after this we will understand some more interesting concepts related to the time period and the frequency, okay, which is again a very important concept. So first you can note this and then we will continue. Okay, so we have understood some important terms related to the sound, related to the compressions and the rarefactions, okay. That is the terms which defines how the sound waves can be characterized, okay. The important points regarding the sound waves, that is the amplitude, the frequency, the time period, and the oscillation, okay, crest and trough. Now let's see the relation between some of these important quantities. So first we will observe the relation between frequency and time period. First we will observe the relation between frequency and time period, okay. So we have frequency as one term and time period as one term, and they have a very interesting relation between them. So let's try to understand. See, if I talk about frequency, frequency means cycles per second or number of oscillations per second. For example, if I say let the frequency of sound wave is f hertz, okay. Let's say I assume that the frequency of the sound wave is f hertz. So f hertz represent that f number of oscillations will be completed in 1 second, okay. So if I say that the sound has a frequency f, then f means the number of oscillations that can be completed in 1 second is f number of oscillations, okay. Now recall the definition of time period. Time period means how much time is required for completion of one oscillation will be known as the time period. So I will say let t is the time period. I assume that, let us say t represents the time period, so it means t seconds is required to complete one oscillation. Okay. So T seconds is required to complete one oscillation. Now observe the relation. I need, for example, if I say use this concept, use this particular statement, f number of oscillations are completed in 1 second. So f number of oscillations will be completed in 1 second. Okay. Now f number of oscillations in 1 second means one oscillation will be completed in 1 upon f seconds. Okay. Just a unitary method you studied in your previous class. For example, 10 toffees worth 1 rupee, so 1 toffee worth 1 upon 10 rupee. So in this manner I can say one oscillation can be completed in 1 upon f seconds. But it is given to us that one oscillation will be completed in t seconds. It is clearly written here that one oscillation can be completed in t seconds. So we have one oscillation in t seconds. So what we can conclude, this 1 upon f seconds also represent the time for one oscillation, and this t seconds also represent the time for one oscillation. It means I can write t is equal to 1 upon f. So the time period of a sound wave is equals to the reciprocal of frequency, or I can write frequency is equals to 1 upon time period. So inverse of time period will give you the frequency, or we can say inverse of frequency will give you the time period. Now what if I multiply it here? T into f will give you 1. So this is another important relation, that the product of frequency and time period is equals to 1. It is always equals to 1. So this is the most important relation between the time period and frequency. Okay. Now similarly we will see one more important relation, that is relation between speed of sound, wavelength and frequency. So we will see an important relation between speed of sound, wavelength and frequency. These three are the important terms. Now what is speed of sound? Speed of sound means the distance travelled by sound in 1 second, or distance travelled by sound per unit of time. So let us say, I will write here, let speed of sound is equals to v meters per second. I assume that, let us say the speed of sound is v meters per second. That means the sound will going to travels v meters in every 1 second. So in 1 second the sound will travel 1 meters. Okay. Now let wavelength is equals to lambda meters. Okay. So lambda is what? It represents the wavelength. So wavelength is equals to lambda meters. I assume this. Okay. Now how we define the wavelength? The wavelength is defined as the distance travelled, okay, the distance travelled by the sound wave in 1 time period. Okay. So lambda represents distance travelled by wave in t seconds. Okay, distance travelled by wave in t seconds, where t represents the time period. In 1 time period how much distance is travelled, that will be known as the lambda. So can I see that lambda is the distance, t is the time period or the time, and v is the speed. So we have a relation that, now using a relation that is speed is equals to distance upon time, I can write that speed of the sound is equals to distance travelled is lambda upon time period is t. So this will give you the relation between the velocity of the sound, the speed of the sound, we can say lambda, which is the wavelength of the sound, and t, which is the time period of the sound. Now observe this relation, I can write V is equals to lambda into 1 upon t. I can write it like this, okay. Just separate this t from this lambda, I write it lambda into 1 upon t. Now what is 1 upon t? In place of 1 upon t, I can write f. So from this I will get a relation that velocity or the speed of sound is lambda into frequency. So it means if I multiply frequency by the wavelength, I will get the velocity of sound, okay, or the speed of the sound. So the relations which are important is this one, that is velocity. Don't get confused with V, okay. V is also used to represent the frequency as well as for the velocity. In some or the other way, just the representation has a very small difference. In case of frequency, we call it as nu, but do not get confused. We will going to use F for the frequency because it will help us to better understand, okay, to have a clarity between, to clearly differentiate between the the frequency and the velocity or the speed, okay. So the speed of the sound is lambda upon t, or we can say speed of the sound is lambda into f, okay. So these two relations are important. Similarly, here we come on this relation that frequency into time period is equals to 1, okay. This relation is important. So you need to remember these three important relations, okay. So this is all about the terminologies related to sound, and we have discussed this concept, okay. So first you note this, then we will continue our topic. Okay, so we have seen the relation between some of the important quantities related to sound. Now we will understand the speed of the sound. We have also related the speed of the sound with its frequency, wavelength or time period. Now let's see how the speed of the sound is dependent on different terms, okay. For example, so speed of the sound, now see what is represented by speed of sound. It represents at which speed or at which rate the energy of sound or the sound energy is propagating through the medium, okay, through the particles of the medium. As we discussed, sound propagates by the motion of particles parallel to the direction of transfer of energy, okay. So that's why the speed of the sound is also a very important quantity. Now it is not like the speed of sound is some infinite, okay. We can observe it from our daily experience that, for example, if we see the lightning, okay, lightning in the sky, once you see the lightning, after a certain point of time you can hear the sound of that lightning. Or you can see when a cracker explodes, after the explosion of the cracker you will be able to hear the sound, okay. Or when the bell ring, once the bell start ringing and after some point of time you will hear the ringing of that bell. It's not like that once you observe the thunder in once you observe the flash in the sky, you will hear the sound. It's like there is a difference between your vision and your hearing, okay. Once you see the sky, the flash, and after some point of time you will hear the sound. So why this is happening? Why is it possible that I can see the flash in the sky first and after some point of time I can hear it? Or why is it possible that once the bell starts ringing and after some point of time I will hear the ring of the bell? Or once the cracker explodes, so first I will see the exploding cracker and after some point of time I will hear the sound of that cracker. It is just because sound travels with a finite speed, okay. Sound travels with a finite speed. Speed of sound is much less than speed of light. Okay. For example, if we talk about the flash in the sky, once the flash happens, once you see the flash, so the moment the flash happens, you can see that. Why? Because the light travels at very great speed. Okay, the speed of the light is very, very large, but the sound travels with a very small speed compared to the speed of light. If I say the speed of light, so then the speed of light is the speed of light is basically 3 into 10 to the power 8 meters per second. Okay, the speed of light is 3 into 10 to the power 8 meters per second. And if we see the speed of the sound, then generally speed of sound, if we talk about the atmosphere, okay, because generally the sound is heard in the atmosphere, the basic medium for travel in which the sound travels is the air, okay, air surrounding you. So in that air, in that atmosphere, the speed of sound is generally 336 meters per second. So just compare the speed of light and the speed of sound. You can see 3 and then 8 zeros, this is basically in meters per second is the speed of light, and the speed of sound is very, very less. Okay, so you can see there is a huge difference between the speed of the two. That's why when the flash occurs in the sky, instantaneously you can see it, but there is a duration, there is a gap, okay, there is a delay when you hear the flash, okay, when you hear the sound of that flash, because sound travels at a very less speed compared to the speed of light. Okay, now as we know that sound is basically a mechanical wave. Okay, why? Because it is using the particle medium for propagation. Okay, but as we know that the mediums are different from each other, the solid, liquid and gas. Okay, for example, if I talk about gas, the molecules are already, the particles are already separated from each other, but compared to in a solid, the particles are very close to each other. So the propagation of sound is different in different media. Okay, so we will say, since sound propagation is based on particles, okay, of the media, hence its speed depends on medium. Okay, so we will say, since sound needs the particles of the medium to propagate, its speed is dependent on the particles, the speed of the sound is dependent on the medium through which it is traveling. It is not constant, it varies from medium to medium, it is different from different mediums. Okay, it is different for different mediums. So what we can say is that the speed of the sound depends on the medium. So the properties, it depends on the properties of the medium. Okay, so the speed of sound depends on various properties of a medium. Various properties means their physical properties, their chemical properties, and there are various other factors. For example, it depends on the elasticity of medium. Okay, it depends on the density of medium, okay, and it also depends on the temperature of the medium. So these are some properties based on which the speed of the sound can be determined. Okay. So elasticity, the density and temperature are some of the factors which affects the speed of sound in different media. Okay. But generally what we will find, general conditions, we will find that speed of sound in solids is greater than speed of sound in liquids, and this is greater than speed of sound in gas. Okay. The general observation is that the sound travels fastest in the solids, then at a medium speed in the liquids, and slowest in the gases. This is a general observation, but do not take it as a fixed observation because there are some exceptional cases. For example, if we talk about speed of sound, okay, speed of sound in rubber, okay, if we talk about the speed of sound in rubber, it is only 54 meters per second. Okay. If we talk about the speed of sound in rubber, it is only 54 meters per second. But if we talk about speed of sound in hydrogen, it is around 1100 meters per second. So there is a big variation. Okay, there are many exceptional cases in which the speed of the sound varies. Okay, it do not follow the general rule. There are many cases, but yes, in general we will follow that the speed of sound is maximum in solids, then in liquids, and then in gases. Okay, this is a general tendency. Now the sound depends on temperature. The speed of sound varies with temperature. Now how it varies with temperature? At 0 degree centigrade, okay, at 0 degree centigrade, I am talking about air. In air at 0 degree centigrade, the speed of sound is 331 meters per second. Then after or for every 1 degree increase, okay, for every 1 degree increase, speed increases by 0.6 meters per second. Okay. So what I am saying is, in air, if we talk about air, at 0 degree centigrade, the speed of sound is 331 meters per second, and for every 1 degree increase in temperature, the speed of sound will going to increase by 0.6 meters per second. So we can say that speed of sound in air is basically 331 plus 0.6 into t meters per second. This is the speed of sound in air. So the general conclusion that we can draw is speed of sound increases with increase in temperature. The speed of sound increases with increase in temperature. As soon as the temperature increases, the speed of sound increases. Now one more interesting case you can see. For example, if I talk about the railway engine, okay, you cannot hear the railway engine if it is far away from you, but if you put your ears on the track, on the railway track, you can hear the speed, you can hear the train coming towards you. Okay, you can hear the sound of the train when the iron wheel of the train strikes the rail track. You can hear that sound. Why? Because the sound is traveling at a faster rate in the railway track compared to the air. Okay, so that's why whatever the sound that engine is creating, you cannot hear in the air, you can hear it in the track or the railway track. Okay, if you put your ears on the railway track, you can very easily hear the sound of train. Okay, so that is just the simple reason the speed of sound is more in iron compared to air. Okay, so this is all about the speed of the sound, and there is one more important thing that we will learn after this, that is the supersonic. Okay, so this is how the speed of sound can be judged. Now it is done because sound has various implications. Okay, sound has various importance. There are various researches going on the sound, as I told you earlier. Okay, so we have to understand that how the speed of the sound varies from medium to medium. Okay, so this is all about the speeds. First you note this, then we will continue.